It took us so long. Are you sure? Are you sure? No, that helped a lot, man. That first solution that we went was wrong. Like I was trying to do it was wrong. Yeah, but it's kind of like a double-edged sword. Like we were doing a lot, and then I feel like we ended up selling wrong. So the second day I woke up and I did different after it, and then I saw it work. I was like, is this it?
No.
No, well, we're a little early yet.
Where the daily.
Exactly. Good afternoon, Jeff. Hey, this one comes every class too.
Yeah. Don't miss a single class. Yeah, when everything is in person.
Yeah.
Yeah.
Yeah, my experience is that no matter how big the class is, whether it's 6 people or 200 people, there are about 6 people who talk to them. And the rest of the people, they just don't exist.
Operating systems, EC3221, and it's just basically just 2 other people that come to class out of a class of like 65.
Really?
So it's just me and the professor just having a conversation every lecture. Every time he says something, he looks towards me and like, do you understand it?
Yeah. I always find people that I watch too. We have nodders. You're a good nodder. I watch you as a nodder. And because a good nodder has to also look puzzled at times, has to communicate. It's harder, but I don't like the math. Yeah, I don't need as many smiles. It's true. If you see it's 2:30, holler.
Okay, so 2 minutes.
2 minutes, excellent. What do you decide? What would you like?
I don't know.
Sorry, I didn't hear what you said. An in-person easy test, right? Yeah. I mean, what's today? Today's March 2nd. Oh, our final? I always, it might be good to write one exam in the class, but it's also hard to do it in 3 hours. Yeah. What do you prefer? Right, exactly. And how much cheating do you think happens?
I feel like in your class, if you try to
It's kind of hard. It's kind of hard. I do make it hard, don't I?
Looking at your steps is not per hour assignment. Like looking at your steps and like having the steps in front of you just keep you forgetting.
Yeah.
That's all you need.
Yeah, for sure. On the next test, it could be we'd be even ready to do greedy by then, All right. It's time. So I think the Zoom is working. If anybody wants to check it, might be good, but I think everything is in order. And All right, so I made an executive decision just seconds ago outside in which we're going to do another example before we do chat. There's a section called chatting about the proof, and let's do another example so we have some more meat to work with. This is certainly a classic example in which we're trying to schedule events, right? So what is the input? The input is a sequence of events, and the only things we know about the event is we know what time it wants to start and what time it wants to stop. And we're going to assume we have one room, and so you're supposed to schedule a subset of the events that don't overlap in time. And we're going to have the cost be the number of jobs that you schedule. So yeah, so then the problem is, given the goal is to minimize the number of maximize the number of jobs, a number of events that you schedule. And at the end, we'll talk about slight changes to it. You can have it be you have a fixed number of rooms, doesn't change much, or you want to schedule all the jobs in as few rooms as possible, right? You're minimizing the number of rooms. All of those algorithms are about the same. You might think some events pay more than others, right? So you could have the input include how much money you're gonna make for the event, and then it turns out that greedy doesn't work, and we'll redo it when we're doing dynamic programming. All righty, so we're just, for the guys who arrived, we have starting times and finishing times of events, and we want to schedule them as many in our room as possible that don't overlap. So let's see how I fight with all of these things up here. Hide panel, hide. I didn't want to hide that one. Actually, that one I was hoping to see if I was in the screen. Oh, floating, hide floating. Hide floating, there. All right, so anyway, you can imagine that time goes one way, and each purple line tells you when it starts and when it ends, and we want to schedule as many as we want. And so in the greedy criteria, the first thing we have to ask is we want to think about each possible event before we know about it. All we know about is a single its start time and its finishing time, and based on that, we want to assign it a real number, and then we will take the one with the best real number, right? So here, oh, got to click there again. So here, the optimal is clearly that. And based on this, what criteria might we choose for our greedy criteria? Yeah, the duration, right? Here we're clearly, it's motivating you to take the shortest event. So the greedy criteria is shortest event first. Motivation, it doesn't take the room for very much time while it gives you a full event, right? Does it work? Look at this example right here. Does the shortest event give you the optimal solution, right? Because you can see shortest schedule is going to give you that, while the optimal is that, right? So I haven't formally proved this, but I would give, I would bet at least a nickel that this algorithm would be too optimal, right? You can see it has this kind of error here. So I bet you it gives you half as many, at least half as many as the optimal, right? And that's a counterexample. So if you want to prove, yeah. Oh, so we're trying to maximize the number of events scheduled that don't overlap in time, right? So the optimal are taking the two green lines, right? But shortest, if you schedule the shortest job first, then you're going to schedule the red one. And when you schedule the red one, you can't schedule the green ones, right? And so that shows you that. So if you want to prove an algorithm doesn't work, you give one counterexample, right? Here is one input in which the greedy algorithm, this greedy algorithm at least, gives you a suboptimal answer. Yeah, right? The optimal solution schedules two events, and yet our algorithm only schedules one event, right? Does that make sense? So we're going to play the game again, right? So what's optimal here? Well, is you can take every other one, right? So who should we schedule first? Yeah, right? Greedy criteria first, starting time, right? Now you want to think, is that optimal? Can you come up with an input in which first starting time is dumb? Exactly. You know, I've had plenty of parties with the guy who comes first is the last to leave, you know. So here, right, that first job might never leave. All right. So here again, you've seen this example before. What do you think this motivates? Which job do you think we might want to? Now I'm going to cheat here. I'm going to tell you what it is because I'm actually going to lie to you. One option is to grab the job that conflicts with its few other jobs, right? It feels greedy, but the truth is it's a cheat because you need to know all the other jobs to know who it conflicts with, right? So it's not formally a greedy criteria, but it doesn't work anyway. So we're just putting it up for passing. Why? So you see, who are you going to schedule first, right? You're gonna schedule that guy first, right? Why? Because he doesn't conflict with all these huge ones or all these ones, right? But that's the optimal, right? Does that make sense? All right. So here are four examples. No, I can't count. We have three examples. Anybody want to come up with the new greedy criteria? We want all we know is the start time and finishing time. And in fact, I'll give you a hint. The guy we're going to schedule is the one furthest to the left that's green, right? What's true about everybody furthest to the left that's green? Starting time, no, because in the second example we did that. Starting time is wrong. Yeah. Finishing time, right? Let's have earliest finishing time. And what's the motivation is let's get in the guy who's going to get out first, right? That's what we care about is when you're going to leave, right? Motivation, schedule the event that frees up the room as soon as possible. All right, so that's our algorithm, right? Here we can just trace through an example, right? He finishes first, right? And then this event conflicts, right? Finishes next, but we can't schedule it, right? And so you can see we sort them by finishing time, and then you take them if they don't conflict with what you have already. Everybody buy that? Yeah.
All of them all at once, right? Not like they come at different times. Because you said you sort them by finishing time. So does that mean that all of those events are present there and then we can choose from any of them?
You mean, do we have the entire input at the beginning of our? Well, there's a very good question. And in fact, had you come to the job interview talk yesterday, it was all about online versus offline algorithms. And an online algorithm is when you don't have the full input until, right? So I actually have a number of papers on this topic too. Jobs arrive and you don't know what's going to happen in the future. But here, this is all offline. You know, right? So in fact, we can suppose it was online, meaning you probably don't know about a job until it starts, right? And can we have an optimal algorithm for that? Oh. Yeah, if you can, that's a good point. Are you allowed to throw people out after, right? So the idea of a greedy algorithm is that once you commit to scheduling them, you can't unschedule them, right? So those are all very good questions, right? Yeah. This guy here? Third. This one? Well, we scheduled him. Oops. And then if we go back here, now we schedule the guy who finishes last, right? And that's him, her, right? Right. The finishing time is how you look at the end point, which is to the right. We want the right point to be as left as possible, right? Finishing time. It's this earliest finishing time, right? Because the duration, we came up with an example where the duration wasn't optimal, right? Does that make sense? All right, so the code is easy peasy. You sort, you have all the jobs, you sort them based on their finishing time, and then you go through them and you commit to them if they don't intersect with what you've taken already, right? So now we have to prove that this works, and that's clearly the harder part. And you can see he's green, so that means I've redid these slides. We start with, so what's his algorithm? His goal is to choose as many overlapping events. His greedy criteria is to short them based on finishing time. The choosing criteria is you take it as long as it doesn't overlap. Here's our example. All right, so remember the game. We're all going to be focused on this game. We jump into the middle of the computation. The algorithm tells us AT minus 1, which once it's done up into time AT minus 1. This picture is an old one. It's actually was in my notes even before I published the book. But here he's committed to taking the guys in the circle, right? And then the fairy godmother comes along and she gives you a full solution consistent with that. One ideally that's optimal, but we're not requiring that of her. And so she has this bigger circle. Oh, look at, it shows you how old it is. This notation is optimal solution consistent with given to us by the loop invariant, right? So we're now calling it ST minus 1, but same idea, right? Everybody buy that? And then at time t, the algorithm commits to the next edge. And as we saw, the next edge is I, right? And here I've just, these are all events that, I guess these ones were all rejected, right? When I said the algorithm has committed to these, the algorithm has also rejected these, right? So she has to be consistent with taking these and rejecting those. But of course, that's sort of redundant because if she takes these, she can't take those because they overlap, right? All right, so then comes in our prover, and our prover is going to want to modify the solution ST minus 1, modify this big circle so that it's consistent with taking I, right? And the solution has to be, the new solution has to be at least as good as the solution she was holding before, right? Everybody following these steps? So, so now we're going back to old slides. I didn't modify these. This was in there all along, right? So what does he say? He says, well, fairy godmother, you definitely have to take event I. All right, that goes without saying because, and now we have to, do we have to modify anything else? Yeah, we have to, there it is. We have to delete any edge she has that overlaps with the one we've taken, right? Yeah, so there it is, right? Because given we added this one, we have to delete that one so that it's still valid, right? And you might remember in the pictures I had before, right? The algorithm took event 6, and I think we dropped 8 or 7 or something, right? Remember we did that? All right, so now we had a paragraph which described how he changes ST minus 1 into ST. And so the paragraph will simply say, take the event that the algorithm took, drop any event that overlaps with that, right? It's a pretty simple algorithm for the prover, right? And now we have to prove that what's been constructed is valid, consistent with everything the algorithm has done, and is optimal, or at least as good as what the algorithm has before, right? So is it valid? Is what she has valid? Yeah, so you have to use the fact that it was valid, right? ST minus 1 was valid. We stuck somebody in who then might have made it not valid anymore, but we made a global statement, drop everybody that conflicts with the one we added, right? So there are, you have to prove 3 things. One, that it's still valid, that it's consistent, and that it's optimal, right? And depending on how you write the paragraph, usually 1 or 2 of those are obvious, and 1 of them is hard. And if you write it slightly different, it switches which one is hard and which one's not hard, right? And when we wrote it to make it valid, right? We said delete everybody who overlaps with it. So clearly, right? Clearly it's valid, right? Does it extend what the algorithm has done? Well, what she had did extend this, right? And clearly we put this guy in, right? But sometimes you have to put, you always have to give lip service to the fact that you didn't mess up the past, right? But here it's actually harder, right? Because your instructions were delete everybody who overlaps, right, with the new guy. How do we know we didn't mess up our past events? Right? What do we need to know? We need to know that this green I is consistent with what the algorithm has done in the past. How do you know that? Well, we don't have to do that. Who does it? The algorithm, right? We know that the algorithm took I, and we know that the algorithm only took I because it didn't conflict with what it's done in the past, right? Right? We don't have to worry about I conflicting with what the algorithm has done because the algorithm might be stupid, but isn't that stupid, right? Right? We added event be consistent with AT. The events in commit do not conflict with I because the algorithm has commit and added I, right? And hence none of these were deleted. All right, so is it optimal, right? Meaning we added, right? It was good, right? And we need to make it at least as good, right? So i.e. if it was optimal, it's still optimal. We're minimizing, right? So we have to say we have fewer or equal the number of events that we schedule. No, we're not. Sorry, this was cut and pasted. We're maximizing, right? We're maximizing. So the arrow's in the other direction. We need the number of events greater or equal to what we did, right? So it's about dropping, right? We added one event. We drop everybody conflicting with it. What we have to prove is that we don't drop more than one event, right? If we delete at most one event, then we're good, right? Everybody got that? Oh, here. What happened to our proof? Pages have been deleted. All right, well, let's go, and hopefully they're not gone badly. Let's go to our old version of the slides. Maybe they're there. All right, be happy with me. You okay? You doing a security check? All right, we're doing event scheduling, and hopefully we still. Oh yes, we do. Here they are. I don't know why these disappeared, but here we are. Proving it's valid. We did that already. Proving extends. Here we are. All right. All right. So we need to prove that we deleted at most one event, right? And so in this example, you know, I always said it's nice to have a picture, but be careful with pictures because proof by picture is a classic bad proof technique because you're just proving that in the picture that you drew, it's true. But you have to prove that it's impossible in every picture, right? But at least in this picture, I'm saying, look at here, 2 possible J's that could be deleted, right? And in my picture, she doesn't have both of them, but our goal is to prove that she doesn't have both of them, right? So here are 2 possible things that overlap. All right. So what are the 2 things? What are the first things we know is that we're not worrying about the jobs from the past because the algorithms handled those, right? We're worrying about these jobs from the future. So by J bigger than I, what do I mean? It means you consider them later, right? And that means their finishing time, right? We sorted them based on finishing time, right? So what we know is that the blue line, which is the finishing time of the 1J, is past the purple line, pinky line, that's the finishing time of I. Everybody agree with that? Because these jobs happen later. All right, and so what do we know about the red lines, right? The red lines conflict with I, right? And if they conflict with I, what does that tell us? That tells us that they have to be running during the purple line, right? Because if they finish later, but if they started in here, then they wouldn't be overlapping with green, right? But they do overlap with green. So that means they're running at the time that I completes, right? Everybody agree with that? Yeah. Oh, yeah, we could be talking about him too. I figured 2 was enough, but you're right. I probably didn't even notice that. Yeah, but you can see the same is true, right? He finishes later. He's running during time, the purple time, right? And what do we know if the 2 lines, the 2 red guys, are both running at the purple time? Is it possible that the fairy godmother is holding them both? Right? It's not possible, right? They conflict with each other. And so she can only be holding one of them, right? And that's our proof that when we added I, we deleted at most 1 event from the fairy godmother, which tells us that our solution is as good as hers. And so if it was optimal, it's still optimal. Right, everybody got that? So here's the second case. The second case is kind of like our second case we did before, in which the algorithm rejects the next event. And so we don't have to worry about the fairy godmother, because if the algorithm rejected it, then what she's holding is consistent with what the algorithm is holding. So why did the algorithm reject it? Because it overlaps with what the algorithm had. So it also overlaps with what the fairy godmother had. So we know that she also must have rejected it. So we don't have to change her solution. Right? Everybody follow all that? Yeah, you good? All right. Multiple rooms. So now it's just switching over to we have multiple rooms, right? And as I said, there are 2 ways of doing multiple rooms, right? The one way is you have a fixed number of rooms and you want to schedule as many events as possible. And the other way is you need to schedule all of your events in as few rooms as possible, right? So turns out that it's not a big difference, right? So what are we doing here? We're gonna, if it fits in, right? Here I guess we have, I don't know what we're doing, but if it fits into our rooms, don't schedule the. All right, so this says, when it overlaps with everybody, right? If it conflicts, basically, if it conflicts with all the other rooms, right, then you throw it away. Unless you're allowed more rooms, in which case you start a new room, right? I think this is pretty unclear, but you can imagine here we have 2 rooms. So these are, I didn't change these slides, so I wasn't worried about the fact that that it was the old one. But we can flip over here. Did I change it? Oh, it looks a little bit. No, maybe it's the same. Yeah, so exactly. I can, if we were doing computer job scheduling, maybe we have 2 processors. If we're doing events, then I have 2 party rooms, right? And so the hard part is when an event fits into 2 different rooms, which room do you put it in, right? If it fits in no rooms, right, it's clear that you either throw away the event or get a new room, right? If it fits into 1 room, then you clearly put it there, right? So the hard part is if it fits in 2 rooms. Here it's fitting into 2 rooms. Which one do you think? Which room should you put it in? Exactly. Exactly. See here, we're gonna put it in this one here because the gap is small. And what's the motivation? Is the new events might want to go in here, right? Right, the smallest gap. Why? Because the next event, if we had scheduled the green at the top room, then the purple room couldn't go. If purple event couldn't go anywhere, right? But if we schedule the green in the second room, then the purple can go in the first room, right? Does that make sense? Putting it in the first would have been bad. All right, so if that's AT minus 1, and that's ST minus 1, which looks the same. You know what? I think I made these live during a PowerPoint, during a pandemic Zoom meeting, so they're not very good. All right, but here is ST minus 1, right? It's consistent with what the algorithm did, and she schedules all these other events, right? And then this is the event that the algorithm scheduled later, right? And so the algorithm puts it here, right? Does that make sense? Why did it put it here? Because it fits. It doesn't fit into those, and it's tightest, right? And so now we have to modify what we did before, right? And so you could say, well, you delete everybody that in the same room that overlaps, right? So it can slip into there, right? But oh, I know. Let's see. Yeah, so that's what you do when the scheduler, when the fairy godmother didn't schedule it, right? So in this case, this event, the algorithm scheduled it, put it somewhere, but she didn't put it anywhere, right? So the proof is exactly what we did before, right? Now the hard part comes when the algorithm puts it right here. The algorithm is putting it here, but she put it there, right? Does that make sense? That's kind of the new case. The algorithm puts it here because you see it's tightest, and she decided she didn't care. She put it in the first room, right? Now we have to modify her solution, right? So to modify her solution, right, the event has to move down 1, right? But if it moves down 1, then where do we put this one? Up. Well, then where do we put this one? Down. And where do we put this one? Up. You're right, exactly. So what we basically do is we take, you see here, isn't that a great animation? You can see myself amusing myself at 2 in the morning. Yeah.
Yeah, so there should be, what if you had like more than one type space?
Yeah, well, so let me describe the change, right? We do what we did before unless the algorithm scheduled some job in one room and the fairy godmother had that same job scheduled in a different room, right? Now we're only talking about 2 different rooms, right? There may be a billion other rooms, but we ignore them. What we do is we take everything in the future in the one room, everything in the future of the other room, and we swap them, right? So now we have to make sure, I mean, it's clearly still optimal because the same number of jobs are scheduled, right? It's clearly still consistent, right? Because we didn't mess up the red and we made the green right, right? So it's consistent. What we have to make sure is that it's still valid. We have to say for each room, right, nothing overlaps, right? So the rooms we didn't change, let's see, do we have, right? So the rooms we didn't change clearly are still good, right? And the red things don't overlap with each other. And why? Because we didn't, yeah, because they were good before and we didn't change them, right? The purple things don't overlap with each other because the fairy, we moved them all together, right? The only issue is does the green, right? Do we have overlaps from the red to the purple and from the red to the green, right? Those are our issues. And so now let's check, does this, why did the green get put into here? The algorithm put the green here. So if you move the green up, right, we're going to say it's going to be fine. Why? Because the why is it fine? Well, it's fine because the adversary had put we know that the fairy godmother had put it up here, right? So right, fairy godmother put it up there, and we are moving it down, and we're moving it to where the algorithm put it. So it's the green won't overlap with the red because the algorithm put it there, right? And so I guess then the danger is that this purple here, the purple is being moved up, and why doesn't it overlap with the red, right? And the reason it doesn't is because it's a later event, right? In terms of that means the algorithm considered it, right? When the algorithm was deciding who to schedule next, let's see, what am I? I'm confused, guys. Let's work on it. Everybody help me here. What is our problem? It's the.
So I guess we are just changing the layers, right? So according to the God, that was consistent, right?
Yeah.
Actually, the second layer becomes more closer to the previous element, right? So that one should be consistent than the previous one, according to our algorithm, not to the fairy godmother. Wait, Chris, are you confused about the second? You're looking at the cat.
I'm remembering now. The green guy can go in both of these rooms, right? And so the algorithm considered putting the green in both rooms, right? And why did it put it in the room that it put it in? It's because it's the red ends later, right? The red ends later. And if the red ends later, and this purple guy here was okay with overlapping with this red. And if we moved it up higher, if we moved it up, well, the gap's only going to get bigger, right? Does that make sense? It's a little, see, these can be a little convoluted, right? But that's the idea. Everybody kind of follow it, more or less?
So the distance between all of the lines is very short compared to the
right. Exactly. All right. Whew. Started sweating on that one. Yeah. Yeah.
So when you spot the purple line on the top, when you put it on the second row, yeah, this one, when you put it on the second row,
right.
Wouldn't it make more sense to put it on the third row? So the extension time is earlier and that is.
Yeah, but then you're opening up a whole kettle of worms. We don't know anything about the third line, right? Our method is, yeah, but then we're going to have to be all these cases, and there's probably not such a, maybe my example here, it happens to be better, but we just want a clean proof. You swap these two, and it's okay, right? All right, what's the running time of this? So we sort the events based on their finishing time, and then you fly through them based in the order based on finishing time. And then for each event, you have to know, does it overlap with anything I have so far, right? I've committed to a whole bunch of things. Now, this new event, do I have to track it with everybody I've committed to so far? No, why not? What? Yeah, just the most recent one. All you have to keep track of is when the most recent one finishes, right? Right, so I had, let's see, do I say something like that here? Right, you only, our new event, you're grabbing it because based on when it finishes, but you ask when does it start, and you compare that with the finishing time of the last one who you grabbed, right? Does that make sense? So that's all very fast. Everybody good with that? Yeah.
You have the green line, which can be both on top and on the second line.
Yep.
So for we move from the top to the second one, actually the purple might not be the optimal solution to stay on the top line. So we need to discuss about that situation, because there might be exist any other lines that's better because the gap is bigger. Right?
Yeah.
So
yeah. See why I'm sweating? It's you had the exact example. That was the exact concern I had. Right? Is explaining that. Right? I think what you're saying is we take this purple and we move it up. And do we know whether this purple overlaps with that red? Is that your question?
No, I mean, it might be another line.
Oh, another room. You're talking about other rooms.
Yeah.
Yeah. Yeah. Well, I think this goes back to, why did the fairy godmother do what she did? Is she optimal? Maybe she could have done something different. And we just don't want to go in and micromanage the fairy godmother, right? All we have to do is make a solution that's valid and at least as good as her solution. Yeah, the first one could go to the third one. And again, the first one's gap is bigger and bigger. Yeah. It depends on what the algorithm tries to maximize or maximize schedule. Yeah, so even in this case, I think the fairy godmother's, well, I'm going to tell you this is optimal because we don't even know which events she dropped, right? And she's not following, I guess this is the bottom line, is she's not following our Grudi algorithm, right? There may be many, many things about what she's done that isn't what we would have done, right? But we're trusting that she gave us an optimal solution, right? So we don't need to fix everything to be right here. And maybe this is answering the question again, is my goal is not to get her ST to be what the greedy algorithm will do forever. My only goal is that it's consistent with what the algorithm has done after time t. Right? Now, when we go to time t plus 1, right, here we're here. What's the algorithm going to do next? The algorithm's going to schedule the next starting time is this one, and it will put this one the algorithm will take this event and schedule on the third line, right? And then we will have to update ST to ST minus plus 1. And at that point, we will swap the first line with the third line, right? Does that make sense? You guys are trying to do it all, right? And remember what I told you about trying to do it all is that you'll panic and drown, right? So just keep track of what my task is. My task is only to change her solution so it's consistent with the past, which is the red, and consistent with this new green edge, right? Don't try to fix all the world's problems today, right? One day at a time. We're just fixing today's problems. Yep. Yeah, we're certainly not down there. People are concerned that this purple should go down here. Yeah. Right, and if we kept going, right, as I said, if we kept going, we would keep fixing all the things that we consider to be mistakes in what the fairy godmother has. But our goal is just to fix one. Right? I think that was a good question, a good answer. Once I kind of figured out what the Yeah, so the reason I'm only discussing 2 is because I'm really only worried about the new event, the green event. And there's somewhere that the algorithm put it, and there's somewhere that the fairy godmother put it. So those are the only 2 rooms I care about. And so I swapped those 2 rooms, right? Because I want to keep my concern, I want to make my life as easy as possible, right? So focus on what is the absolute minimum I have to do to change the fairy godmother solution so it's consistent with what the algorithm has done, right? And not do too much, right? Oh, is it? All right. Right. If the gap's all the same, flip a coin. It doesn't matter. Yeah. Should be the same, right? Exactly. And one sort of a meta idea I have when numbers are equal, and you're choosing between them, is that all options should work, right? Because an adversary, you're assuming an adversary is giving us this input, and the adversary could have added a little infinitesimal to each of the numbers so that you would have sorted them the way the adversary wanted you to sort them. So it better work for all of those, right?
We should put the green van moving into the next part of this gap from the next one.
ST isn't the algorithm, that's the solution from the fairy godmother that we're adjusting. The algorithm is AT, so we don't actually have the top and bottom. The algorithm is only as far as the green line. We haven't considered the purple line. Purple lines are in the future, which we don't know
about.
Don't care about.
Exactly. Exactly. So if you're the algorithm, what he's saying is exactly true. The algorithm knows about the red and the green. And why did the algorithm want to keep this gap as big as possible? Because the algorithm doesn't know about the future. And the future could come up with could be some event that comes in through here. Right? So in fact, the reason the fairy godmother put the event green here is because the fairy godmother knew the future. She knew no event was going to be coming here, right? But the algorithm doesn't know whether an event is going to come in here. And so the algorithm is forced to put green on 2, just in case the future brings something, right? So if you ask, why doesn't the optimal do what the greedy's doing? Because she doesn't have to, right? She knows the future. She can do whatever she wants as long as it's optimal, right? I guess that's kind of what we're trying to prove. It's locally, it feels putting the green here is the best thing to do. But we have to prove that globally it doesn't matter, right? What are the long-term consequences? Maybe it was bad to do this. And we have to prove that no, it wasn't bad, right? No matter what the algorithm, whatever the future brings, whatever the optimal solution for fairy godmother wants to do, we can always say it wasn't bad for us, right? Yeah. Well, no, we already, no. We're just trying to prove that this step, the step of putting the green guy here, instead of here, feels locally optimal. And in the new slides, I'm defining this idea of globally optimal, right? I'm saying it's a globally optimal step because no matter what the future is, my potential isn't getting worse, right? But it doesn't hurt me to put this here. It may help me, but it will never hurt me, right? Does that make sense?